All right. Well, yeah, it's 12:01 here, so we'll go ahead and get started. So welcome to our FlowEFD webinar. And today we'll be looking at FlowEFD in terms of electronics cooling. And this is our second webinar within our FlowEFD webinar series. And I'm happy to share this with you today. And FlowEFD is a general CFD tool for designers, typically for design purposes in the overall engineering cycle. Just a little bit about me, your presenter today. My name is David Stevens. I'm a technical pre-sales here at Maya HTT. And I have 7 years of applied CAE experience in turbo machinery, heat exchangers, thermal systems, and that was mainly structural and CFD analysis. Maya HTT, a little bit more about us. Maya HTT provides software-driven engineering solutions. We've been awarded this year the #1 worldwide partner for Siemens. We're passionate engineers. 75% of our staff are scientists and engineers. Although we started in space, we're recognized worldwide for our simulation experience and our overall engineering experience applied to many domains and areas across engineering. And we really kind of do it all, from anything from in space to things here on the ground, even tomatoes. And beyond just a value-added reseller of Siemens, we've also written 30+ software modules for Siemens. As I said, it's not just simulation that we do here at Maya HTT. We also do design, manufacturing, more and more AI, IoT solutions nowadays. We also do software development and custom applications for things like NX, and also including optimization and automation, excuse me. And finally, product lifecycle management as well. So as I said, we're the #1 value-added reseller for Siemens this year. So all of our solutions incorporate the SimCenter and Siemens portfolio, and obviously today we'll be looking at the CAE portion of that. The CAE portion for simulation and Siemens really encompasses everything. We're a true multi-physics solution. Anything from structures, dynamics, electromagnetics, additive, motion analysis, even safety, and of course thermal flow that we're looking at today. So this is our hands-on simulate series, as I mentioned, and we already did an introduction last month for introduction of FlowEFD, which is a fairly detailed introduction for all of the basic components of FlowEFD from start to finish, where we looked at an IGBT cooling module. And today we'll be looking at cooling for electronics specifically. So we'll be doing an overview of the electronics module, looking at a detailed analysis of a PCB. Today's demo will be a little bit faster, when then afterwards we'll go into looking at some of the more specific applications for thermal cooling of electronic components. And then our other 2 webinars coming up, we'll be looking at SimCenter FlowEFD for electronic vehicles. And after that, we'll be looking at SimCenter FlowEFD for building simulation, specifically HVAC systems. In the demo there, we'll be looking at a flow analysis to optimize temperature comfort within a room. So today we would like to do about 4 or 5 questions just to learn a little bit more about your needs and how we maybe can help you and learn a little bit more about you. So we'll go ahead and launch our first poll right now. So really this poll we're looking at, just want to get an idea of our audience here and their experience using CFD analysis. Do they currently use CFD analysis right now for any of their design cycle work? Do they use it, during the early on in the design cycle phase? Do they use it later on, or do they only really do it at the end? Or do you use it all throughout your design cycle? And that's really probably optimally what we would like to see. So most people here are saying don't seem to have done much with CFD, and FlowEFD is a fantastic introduction for anyone who has not done CFD analysis before or is just looking to implement it in their work. So just a quick little agenda. We'll be looking at what is front-loading CFD. That's what we're really focusing on today in terms of how FlowEFD is used for designers. And we'll do a quick overview of FlowEFD, then we'll jump into our live demonstration. And then after that, we'll take a little bit more of a detailed look at some of the electronic cooling special features, and we'll finish up with a Q&A. So electronics cooling, why is it important, and how is it specifically relevant today? Obviously, we look around today and we're seeing more and more electronics devices that are integrated to every part of our lives, whether it's the smartwatch on our wrist that's automatically connected to our cell phone, which is then connected to our car, and our car is connected to a multitude of sensors that are used for safety systems, or even to our screen on our refrigerator. Everything nowadays is becoming electronically integrated with smart systems. Therefore, there's a more and more of a need to make sure that these systems are reliable and have long longevity and can be used for years to come. And certainly, one of the biggest issues with electronic systems has always been temperature. The #1 cause of failure for these electronic systems is temperature induced. In the past, we would still see a lot of dust, humidity, vibration as well. And as we know nowadays, all of our phones, you pick up a phone now and it's like, oh yeah, I can drop it in a glass of water and it's fine. It's completely hermetically sealed. That does keep out the dust and humidity. However, that can cause issues with temperature because it's harder to cool something that isn't open to the environment. So it's more and more important today that we're able to look at the thermal behavior of these devices. So based on that, manufacturers worldwide have the same challenges as we move into this more and more digital and electronic integrated world of devices. And first of all, the main things that the designers and engineers want to create is lower development costs. Really, the age-old problem is that, well, I want it fast, I want it cheap, and I want it good. And often the thing has been, well, you can only have 2 of those. But manufacturers and companies now, we want to be able to have all 3. And simulation is one of the ways that we can really drive towards that. So we want the faster time to market, we want the lower development costs, and we want more intuitive, better performing products. But in order to do that, we need to eliminate bottlenecks in the design process. And simulation can certainly be a bottleneck in the design process. I think the term I've heard before is analysis paralysis. You can analyze these systems to the nth degree, but at the end of the day, you do have to generate a prototype. But we really want to do a lot of that system simulation and, engineering simulation early in the design cycle, and that's what front-loading simulation is. Along with that, we want our products to have lower risk, and that's another reason we want to do things early in the design cycle. And we also want to be able to hit compliance numbers for certain regulations and standards. So just to, as I've done a primer to it here, but what is front-loading simulation? Well, if we look at the design cycle and time it takes to create a product from nothing, a white sheet of paper, to a prototype and then something that's on the market, there's a certain time it takes to do that. And also there's certain levels of effort depending on what we're trying to do. Early in the design cycle, those efforts to make changes in the design are relatively low. And that's great. We like to be able to do that. However, as the design progresses, the cost to fix these defects or things that we find are much, much harder and more costly. So, that's where we really want to drive our front-loading simulation or put our simulation early on in the conceptual and preliminary design phases so that we can really nail down and get our design in a very stable and solid place before we move into creating prototypes. And so we don't want to identify those defects later on in prototype design. We want to identify those defects early on here as we're doing simulation. And that's what front-loading simulation is. In terms of an electronics application for front-loading simulation. What is FlowEFD and how is that applied to front-loading simulation? As I've stated previously, front-loading is the concept of performing your simulations early in the design cycle to maximize the impact and catch issues before late-stage validation. There are several features for FlowEFD that differentiate other tools on the market, and this slide aims to highlight some of the key features and functionalities. FlowEFD is a general purpose tool which can be used at a wide range of flow and heat transfer problems, and even more than that we'll see on the next slide. It's been specifically developed for non-CFD specialists, so this is for designers mainly, but really this tool can be used for experienced analysts who really want to get a whole bunch of preliminary work done quickly before taking it to you could say a more traditional CAD tool like StarCCM. The Mesher and Solver have been uniquely designed with proprietary technologies which facilitate streamlined CAD embedded analysis rather than something that's much more obscure or third-party technologies. The result is a dramatic reduction in the barrier of entry and overall CFD simulation time. The tool is available in 5 versions to support CAD workflow. And today's demo will be looking specifically at the NX version. So as I said, there's tons and tons of applications where FlowEFD is relevant. Today, obviously, we'll be looking at electronics cooling. But you can see here that there's really runs the gamut here, everything from combustion to complex cavitation analysis to aero heating and even supersonics. We can even look at things like rotating equipment or real gases or free surfaces. So it's really a very broad tool that can be used across all applications. So we talked a little bit about and mentioned CAD embedded technology. And what does that mean? What does CAD embedded mean? Well, if you're a designer, you're generally used to using at least one CAD tool. And if you're used to using that CAD tool, it's very intuitive for you, and you really are fast with it, and moving over to a new tool takes a lot of time. So first things first, the pre and post processing of the simulation is completely done within the same CAD environment that you're used to. Beyond that, there's also a direct link to the geometry that you're working with to the simulation. This facilitates changes as well as optimization, and we'll look a little bit at optimization at the end of our demo. Also, results are shown in context of the CAD models. You're not looking at some obscure plot or something like that. It's all very intuitive and shown on the CAD geometry. And as I mentioned earlier, it's a native familiar CAD interface. It's something that you're used to. And finally, with FlowEFD, one of the major features is that there's no need to simplify the CAD geometry. You're not making major changes to your CAD geometry just to perform the analysis. As you can see here, we have different versions that support multiple CAD environments. As I said, we'll be using the NX version today. We also support Siemens Solid Edge, PTC Creo, as well as Dassault's CATIA. If you don't have one of those, there is still a CAD embedded version that has its own CAD model within it, within the FlowEFD standalone version. So immersed boundary meshing, and that's, if you've known anything about CFD and you've used some traditional CFD packages, this might sound completely different, and it is. When I first started using this tool, it surprised me and it wasn't what I expected, but compared to what I had seen in the past. And FlowEFD uses immersed boundary meshing. So when you're creating a CFD model that is using conjugate heat transfer, which includes solid and fluid domains, there's one entire continuous mesh throughout the entire domain, and fluids and solids are automatically separated using Smart Cell technology. In the Smart Cell technology, you can have multiple fluid and solid domains within a single cell. So one of the great things about this immersed cell technology is that it is all 100% Cartesian grid cells. You're not using tetrahedrals or polyhedrals, and this helps to keep the mesh count extremely low and do efficient calculations. And traditionally, you would have to, for a regular CFD analysis, you would have to simplify your geometry, extract your fluid volume, mesh the fluid domain, mesh the solid domain, and this would take a lot of iterations. You'd have to be worrying about inflation layers to fully resolve viscous sublayers and things like that. In FlowEFD, there is none of that simplification, or excuse me, there is all of that simplification automatic in the system. You don't have to do any type of geometry changes. It's an immersed hex mesh. It's robust and it's efficient. You can also introduce things like automatic refinement based on flow gradients, but it's also not a black box either where you don't have any control over your meshing. You are able to impose local mesh controls like we see here where we're having a real small cavity of flow, and so you really can customize it as well. And looking just a little bit more at that technology, we have specific technology for wall functions that help to model that viscous sublayer without creating inflation layers, which makes these solutions extremely efficient while at the same time accurate. We have the ability to model thin walls and multiple areas of different solids through a single cell, and there can be up to, I think, 36 different solid properties within a single cell. So if you have lots of thin little structures or things like that, you don't have to have individual cells for each one. We also can model thin channels using relatively small number of cells. And even though we're using this immersed type of mesh, we're not doing major things to try to simplify and mess with the geometry. We're keeping the same geometry. We do not need to simplify, which is a major time saver, but also helps with accuracy as well. So how is this applied in the electronics industry? As I kind of mentioned earlier on, where we were looking at examples of all of these smart devices and electronics being integrated into everything, that's certainly the case here. We looked at an IGBT in our previous demo. That's certainly applicable to an electric vehicle or some type of renewable energy application where we're transporting very large amounts of power and energy. Same thing extending from that to maybe charging for vehicles, or maybe a wireless charger for a cell phone. And certainly going into cars as well, sensors and LiDAR, and that kind of goes into what we'll look at in our demo today, but still traditional things like electromagnetics and a permanent magnet generator, medical devices, and traditional PCBs as well, which is all just a part of all of the smart technology. So we'll go ahead and jump into our second poll. And we'd like to know a little bit, if you've done CFD analysis before, what are some of your challenges? We would like to know. That's, sometimes people see CFD and they get a little intimidated, and they see all these steps to do and they worry about convergence, and it can take a lot of work to do some CFD analyses, and that's what we're really trying to reduce. So we'd like to know a little bit more about what plagues you in those realms. But really today, we're hoping that you'll see that the CFD through FlowEFD can be extremely efficient and intuitive for a lot of users and designers, regardless of your experience level. So from there, we'll go ahead and jump into our demo in the software. And today's application that we're looking at for electronics is an autonomous sensor fusion box. And one of the things I mentioned that we've seen in our previous slides is that autonomous vehicles, autonomous hardware and devices are becoming more and more common. And well, in order for those devices to work, they need to process a lot of information that comes from cameras, LiDAR sensors, those types of things. And it needs to do it very quickly and very efficiently and very reliably. So these systems need to be kept very cool and within their design specifications all the time. That way they are reliable, but also they need to be able to handle a lot of data. And in this system, the example we're looking at today was designed from a example that had the processing power of 150 laptops, supported 12 cameras, and multiple LiDARs, and with an overall performance of 8 teraflops of floating point operations per second. And so this system here, we have a PCB containing a high power density electronics that is sandwiched between 2 cold plates. We have our coolant lines, and then going down to our other enclosure here with our pump, our radiator, and our fan. Go ahead and jump into the demo. Get our software open up here. All right. Bear with me. Okay, here we go. All right. Looks like everybody should be able to see my screen here. With if you can't, please shoot something to me in the chat. But here we are. We have our model in CAD here in the NX environment, and I'm just going to go ahead and jump back. Actually, I don't even need to do that yet. But here you can see we have our overall assembly tree. We have all our constraints for this entire system. So CAD, the NX CAD environment is completely seamless and integrated within the NX environment. And I am already in FlowEFD. It's easy to jump into FlowEFD by simply going to our file, applications, and simulation, and we're already in FlowEFD, or we can just hit Control-Shift-F. So we have our model here, and we'll just do a quick little cross section to take a quick look at some of the geometry. Let's do a quick clip section here. And you can see that we have some overlapping and interference geometry between this hose, this connector, and this manifold. And FlowEFD doesn't care about that really. It completely works through that by using something known as material hierarchy. So you can set a material hierarchy that says that any interference that has between these two materials, aluminum comes first, or the rubber comes first, or something like that. And when it meshes it, it'll completely remove those issues. You can also see here in this model our cross section through our cold plates, as well as part of our PCB, our radiator, etc. We'll go ahead and hide that section. I'll go ahead and jump into modeling real quick, and we'll look at our heat exchanger, make our work part. Just open that in a new window. So we have our heat exchanger here. I'm going to get rid of that section. And we also have our expressions for that. So within the CAD environment, FlowEFD has access to all of the CAD expressions that are defined within NX. And this is going to be extremely important when we start to look at things like optimization, where we can run simulations that will automatically change these dimensions and create geometry and create simulations and outputs based on that, so that we can do parametric solves and optimization. So if I jump back here to our overall assembly, one of the first things that we would need to do is just define the overall parameters of our analysis. So if I go to my demo start example here, we have a couple ways of starting this. We can do this through a wizard. If I go over to this flow analysis tab, which is the FlowEFD, I can do this through a wizard. And in here, I would define my project name, certain configurations maybe for the assembly. But in here, I would also define things like what the type of fluid would be for default, type of solid materials, what type of physics I would be using, radiation, conduction, fluid flow, all the possible physics options, and as well as my initial conditions for the analysis. And the last thing I would define would be a default surface roughness for surfaces their flow is going. But today we'll actually be looking at just using a simple template to create our analysis. So if I want to already have an analysis, and I'm doing maybe a lot of iterations on this, and I have a template that I can set up for it after I've done my first analysis, and that's a really easy way to create these new analyses. And let's say I'm creating a new project, I can hit new, and I have the sensor fusion box with heat set up, where maybe I'm doing I start off an analysis and then I'm doing a parametric study afterwards. Once I do this, my project is automatically created. So that's fairly straightforward, just kind of creating a project like that. Maybe we want to do it manually too. We can just go into general settings and we can select our fluids or solids. We can do it manually as well. We don't have to use the wizard. So I'll just go up to my completed run here. And so once we've done that, we can look at just some of the couple things that are defined, that we defined early on, which we have boundary conditions for this system. And one of the things that we have here is a water cooling loop that's a fluid subdomain. In this case, we have a fluid domain for the air, and we have a fluid domain for the water. In this case, the water is going to be a fluid subdomain. And this is really easy to define. All we have to do is select one of the surfaces of the fluid domain, and it will automatically create the geometry, or I should say just the fluid domain based on the enclosed geometry. And FlowEFD has the ability, if you have issues with a leak somewhere or something like that, it can find it. One of the things we can jump back and do is just show how, if we had just imported this geometry, we can check it really easily. So we have this check geometry option here, where we can run a check on our geometry, make sure that if it's an internal flow, that we don't have any leaks. And you can see here that it found one little issue, but it fixed it. And so that's kind of a testament to the ability for FlowEFD to handle dirty geometry. But we can also show our total fluid volume here and make sure that that looks correct for what we're trying to simulate. So we'll just close that up. So we have that fluid subdomain. We also have our fans that are predefined. In FlowEFD, you don't have to do some crazy, boundary conditions to try to define a fan. There are tons of fan modules within the database. So in here, we can just look at our fan 1, which is for our air fan, and then we have an internal fan, which is for a pump. And we can do, like I said, grab something from the already defined database, or we can input a custom curve. We can just show how to edit that real quick. And this is all within the engineering database, whether we're looking at perforated plates or porous material, radiated surfaces, or fluids. There really is a fantastic database here with a lot of depth. But this table and curve for this fan, we have a specified pressure drop versus flow rate curve, and that can be automatically used within the analysis. So we have those defined. You can see though here, we don't have any heat sources yet. We don't have any radiative surfaces. We do have this air filter, which is porous media for the inlet, which is kind of important because that's going to definitely produce a pressure drop and restrict the flow a little bit, but it is necessary for the design. So, but from here, one of the things that we'll want to do is use the EDA bridge to import our PCB data. So in order to do that, I just go up to my tools and I just go to my EDA import. And this opens up the EDA bridge, which allows us to bring in EDA data using standard file formats. Today we'll be using ODB++. And so I'll just go ahead and do that, grab my ODB++ file. We also have the ability to use CC or CCE, IDF files, ProStep, as well as a couple other options as well. So open this up, use our default component heights, etc. for this demo. And this just takes a second to load all the data. And this, you'll see, is not a trivial PCB, and this loads this data quite quickly. All right, so we can see our PCB here. We're on the first layer, and you can see up here in our tree, we have the different layers. We have the overall PCB board, and we have different ways of modeling the PCB board within FlowEFD. We can do different modeling levels. We have a detailed model, which includes most of the PCB layers and components. We can also do just a simple compact model, but then also we have the ability to do a material map, which is what we'll be using today. And the material map basically creates a resistor network to model the PCB instead of doing a real simple design, compact model that is much more simplified, or doing a very detailed design, which is going to be more detailed, but is going to be computationally more expensive. In this case, it's kind of the best of both worlds. So we'll be using material map, and from there you can see the different layers that have been imported. So we have our dielectric 1, our looks like a ground layer here, and then we have our other dielectrics and other layers. So you can see and go down through and see all the detail. Then down here we have our active components that have been imported. Then we'll have inactive components here in a second once we filter out some of the things that we don't need for the solution. We also have our power and ground nets defined as well. So if I go over to our filter here, you can see that actually, yeah, I'm actually filtering out some components right now. And if I turn off the filter though, you can see all of these much smaller components. And these are really not relevant for this analysis. We're looking at second, third order effects here. So we'll go ahead and keep that filter on. But we have the ability here to filter based on dimensions of width and height, power density, and even hole size for really reducing the computational burden and the detail of these PCBs if we don't need them. But like I said, we'll keep that filter on as at the default settings that we have here today, and you can see what we're including in the model. So you can see we have, these are our active components, but notice there's no power assigned to these yet. We need to import our power data for those, and we have our inactive components here. So we'll just go ahead and do an import of a thermal list. But before I do that, I'll actually show you the thermal list. So a thermal list, we're able to basically assign power, and these are used as a reference designator that are also tied to CAD, the model type, whether or not they'll be filtered out. We also can look at the max T junction, the maximum case junction for the ICs, also the resistance of the components, and then finally the power for each one. I'm just gonna minimize that, and then we'll import our thermal list. And we can do Excel files, CSV files. Today we'll do a CSV file. And you can see now we have power assigned to our components. And look at the active components here. You can see the power assigned to each one, and then up at the top here, you can see our total board power. So that's the thermal load that we'll have to deal with here. And our big one here is this central IC that produces 200 watts. There's different types of models for these ICs, from very simple volume thermal loads to, in this case, we'll be using a 2 resistor model. FlowEFD also has the ability to use an N resistor model. And then finally, there is the ability to model this as a very detailed package with the conductors in it, etc. And I'll show you a little bit about that here at the end. So depending on what fidelity of analysis you want, you have options for that. From this point, this is where I would just hit transfer assembly over to FlowEFD, and this would transfer it over and create something called a smart PCB. And I've already transferred that over. It only takes a couple seconds, but if I try to transfer it now, it'll create an issue because it's already there. So we'll just close this up. I'm not going to save it because I've already done it. And if I go to this drop down here, which says from components, and from components means these are things that I've imported from the EDA import. So the EDA has imported the materials for the plastic packaging, the insulator, in these components, but also it's automatically created volume heat sources for these smaller loads. Just turn it here so you can see it a little bit better. And also we've already set up our radiative surfaces, and then more importantly, we've created a 2 resistor. Things lagging a little bit. A 2 resistor component for that main IC, and then we have our smart PCB here, which is the model that we looked at, which is this time a multi-material model. We were able to define our dielectric material as FR4 and our conductor material as copper. And we can change things like fidelity and things like that. But we can also view our layers that have been imported. And these are not explicitly modeled. They're actually part of the smart PCB model. But you can see here that all of our layers are contained within the model. So from there, we also here actually have a goal that we'll look at here in a minute, but that's looking at the IC junction temperature. But before we look at that, let's talk a little bit about the mesh that's been generated for this. And as we've said, that FlowEFD uses Cartesian immersive meshing, and it still solves the same Navier-Stokes equations, still looking for resolving the solution and looking at residual values within the discretized solution. And so let's look at our mesh. We still need a mesh, and we go here and just close this up. And fluid subdomains, and then we have our global mesh here. And we can edit that definition. We can do global mesh here. As I said, we can do refined local meshes too, but in this case, we're just using a large global mesh that has some automatic refinements in it. And I'll just switch over to the automatic. So you can see if I show the basic mesh here, we can start with multiple values of an initial mesh. In this case, we're starting with an initial value of 3. And FlowEFD has the ability, based on passage size, curvature, things like that, to resolve the mesh at 9 levels below that. So when I say 9 levels, it'll, a level of 2 below this would subdivide this cell into 4 cells, and so on and so forth. And we'll take a look at that here in a second. We also have the ability to do a manual mesh to say if we want to bias it in the X, Y, or Z direction. We have the ability to influence channels more. We can do more refining cells on fluid cells and on solid cells, and as well as fluid solid boundary locations. So it automatically detects that boundary location, even though the cells are one and the same. And we have some advanced refinement options here, and as well as things for small slots. Today we've automatically generated our mesh using this third level, and we are showing our basic mesh here. Close that. I'll hide my geometry here so it's a little bit easier to see our mesh. And if I go to my results, this is going to be a version. Let's jump over to our mesh. Not quite at results yet. So our first mesh here that we'll look at is just a mesh through the body of our heat exchanger radiator here. And you can see that we have some refinement. This first level mesh is actually, looks like it was done on a level 4, not a level 3. And this is a level 4 mesh to start. And then in these areas, it's refined down to 1 level of refinement. And this is done, as I said, based on curvature, passage space, and what else? Possible fluid solid interaction, etc. So that shows that. And then if we jump over to, we want to look at the mesh on the actual solids, what it looks like. We can show the mesh. This is what the smart cells look like, where it's subdivided cells, and these are smart cells that are shown on the fluid solid interface here. And this can be made much finer depending on what level of fidelity you need. But for this case, of these type of pipes, this should be perfectly sufficient. We've shown mesh. So let's say we were ready to run this solution. We can change our solution options here. We can change our goals, and goals are really how we monitor these solutions. So in a typical CFD analysis, you would always want to monitor relevant design variables, let's say pressure drop, heat transfer rate, the coolant temperature, the IC temperature, and we want to know that the solution has converged when, in this case, a steady state analysis, these values have stopped changing, they've come to a steady value. And that's really what we monitor in these solutions, and that's what the convergence algorithm looks at. And in this case, so we can define multiple goals for convergence. And in this case, one of the first things that we've done has been automatically defined is the temperature of the junction in the large IC. And we want to make sure that that temperature is reached a nice steady value before we consider this solution converged. Additionally, we have goals for our, sorry about that. We have goals for our inlet temperature, our inlet fan pressure increase, the outlet temperature of the cooling loop. We also have some more goals here that are actually just related to for the optimization of the system, where we're going to be looking at trying to minimize the mass and size of the system while keeping the IC temperature at a similar value. And we also have an equation goal here, which looks at the temperature delta in the system. So you really, have a bunch of goals to define here. You have global goals for the entire system. Maybe you want to know the maximum temperature anywhere in the entire analysis. Point goals, maybe you're looking at a temperature at a specific location or velocity at a certain location. We have surface goals, what I just opened. Maybe you want to look at the average value of velocity at the inlet of the fan or the inlet of the air intake, something like that, or maybe a average surface temperature somewhere. And then finally, we have volume goals that can be defined for a specific volume, whether it's a fluid domain or something like that. And Any of those goals that we mentioned can then be used in equation goals. Maybe we have a pressure here and a pressure at the pump inlet, a pressure at the pump inlet, and then we want to know what the delta P is across the pump. So we could define an equation goal for that. So once we've solved this solution here took about 30 minutes to solve on a workstation at the current mesh conditions. So very, very efficient solve for something this complex, where you have multiple fluid domains, small passages, and small intricate features like the fins on the radiator, etc. That's a very fast solution in terms of CFD. And as I said, we look at the calculation options if we needed to change anything. As I mentioned earlier, we do have the ability to define automatic mesh refinement within the solution based on flow gradients. We didn't do that here. Maybe that'll be mentioned later. And we can define custom convergence goals as well. So this has been solved, and the next thing that we want to do is kind of take a look at the results, which you kind of got a peek of earlier. And so I'll just hide my geometry again here, go back to FlowEFD, and look at our results. So we can define a lot of results here that are kind of standard CFD results. We can look at cut plots, where are essentially a cross section through the model. In this case, we'll look at a cross section of temperature for the fluid as well as the solid. And we're just doing a quick cross section here through, this goes right through the radiator and the fluid pipe within that radiator, as well as the fan and the pump. And we can animate this really quickly just to show the overall temperature change through the entire system. And it's just going to sweep up and down through. So our PCB show everything. And we can easily change these values if we want to look at the velocity just by stopping this. And you know, if I wanted to change this, I can change any of these values just by a quick drop down. The other thing we can look at here, hide this, is we have surface plots, which are on the surface of a body, not cut through. And let's say we want to look at, well, more importantly, we're looking, you know, really the goal of this analysis is looking at the PCB design. Let's go ahead and show the surface temperature of our PCB. And you can see here that our PCB overall is looking really good with fairly low temperatures. We do have a kind of a high temperature here on these two chips, and maybe, who knows, maybe we want to change to our cooling plate that has a, you know, outcropping to it that touches those components to cool them off a little bit more, because 98C is a little bit high maybe. So that kind of shows that. We can also look at the temperature of the PCB, or excuse me, the coolant temperature loop. So we can look at the actual temperatures of this radiator, the hot and the cold side. And we can also take a look at the enclosure. So we have an overall temperature look at the enclosure here, where we get our hot pipe and our cold pipe for these. And maybe we want to know, okay, is you know, this pipe getting too hot based on the material? You know, if this is some type of rubber, is it going to stand up to that temperature? We want to know that. Let's go ahead and hide those. We also can look at flow trajectories. So we can look at the fan flow trajectories in context of the geometry here really easily. Oh, I don't think I have those on transparent, and I'll have to do a little work to change those. Excuse me. We also have the flow trajectories we can look at for the coolant pipe. So we can see the temperature as well as the flow trajectories within the system for our coolant pipes. And we have some other things. We can do particle studies, we can do point parameters, we can look at surfaces. We can do XY plots. Say you want to look at pressure drop certain location through a pipe, or temperature across a certain location with a specific sketch that you've defined, like a line. You can do that. We can also look at our goals that were defined for the solution. And because we wanted to make sure that these goals were hitting steady state points, and we can just go ahead and show those real quick. And we can view a summary of those first. We can look at the delta T, and these are all based on the goals that we previously defined. And we can say, okay, was this goal used in convergence? What was the change? what was the criteria that was needed to meet convergence. We can see all that data. We can also see a plot here. And some of these, it looks like, oh, maybe we need to let this solution run a little bit longer. Maybe it's starting to flatten out. This one's pretty flat, but maybe we need to say, okay, maybe we let this run 100 iterations. Maybe we say, well, let's run it another 100 to make sure that it's really, really converged. It's close, but then we can do that. So this really helps with that. These can also be seen during the solution run. So you can define cross sections as well as plots like this to be seen during the solution, so that you can make sure that this is, it's not a black box while the solve is happening. You can see what's going on to make sure, okay, this is going in the right direction and I don't need to make a change before I spend a whole bunch of time solving this. All these can also be easily exported to Excel. Really neatly too, it does everything. It gives you your summary, it gives you all of your plots. That's a mass that's going to be constant, our delta T. It automatically creates these nice plots for us if we need to put these in a report or send them to a customer. And also, speaking of things that maybe we want to send to a customer, we have the ability to create these nice reports that are really easy. Maybe you want to create your own template, but also FluentAFD has their own quick templates. In this case, we'll just do a full report. And just takes a second to run. And then we create this nice report. I don't know, let me make sure you can see that. And we have this nice report that's been generated, including all of our system information, all of the input data for the analysis, etc. Let's jump back to NX here. And we're done with that report. Lastly, within this little environment here, we can also export results. Maybe we need to look at some stresses in that little heat sink, or I should say radiator. We need to make sure that we're doing okay with that. So we can export these to a structural solution or to some type of external viewing if we have something else we want to look at, special rendering or something like that. So lastly, one of the things I mentioned earlier was the package creator. And we'll just take a quick look at that before we jump out of this. And I'm just going to hide these. And we'll just jump into that super quick so that we can get back to the end here. But we have a package creator. And this allows us to do very detailed, explicit models of ICs. And take just a second to come up. And it creates, really, we'll actually just give this 1 second. I'm going to open. Apologize for this. Well, I'm not exact. Oh, there it is. It opened. It just took a minute. All right. So here we have our package creator where we can create some really detailed models. Of course, it opened a bunch of them. Models of our ICs. And let's just say we want to create a new IC here. And we have our recent ones, but we also have the option for all, whether it's a MOSFET or another type of IC. And let's say we want to just do a QFN here. And we can just give it a standard name. We'll just call this QFN2. And standard outline, we'll do a 4x4 millimeter and maybe 16 leads. Let me just go ahead and set our next step here. And we want to have this as a thermal design power of 1 watt. And our die length and die width we'll keep as the default 1.8. And our package thickness type we'll keep as thin. And we'll just go ahead and hit create. So now we have a very detailed model of this IC that we can import directly into our CAD and into FlowEFD and get a very detailed analysis of this. If you can see, I'll just kind of hide the encapsulant here or make it transparent, where you can see your individual conductors. You can change the material. Oh, looks like someone can't see anything for Package Creator. I apologize. Should be able to see it now. Sorry about that. Maybe Talia will be able to edit that out. So here we have our Package Creator. Sorry you couldn't see the earlier part, but here we have our package that we've defined pretty easily. But we can change our different types of materials for bond wire, whether in this case it'll just be gold. But really you have some very detailed design variables for these. And as I said, this can be automatically imported into the analysis, into your CAD, and fully accounted for in the thermal analysis if you would like it to be. And I have a slide showing that a little bit later. So for now, we'll jump out of this and we'll go back to our PowerPoint. And we'll jump into our third poll. So, right now, okay, well, is your work relevant to this? Do you do electronics analysis? Do you design electronics in your business? Are they integrated within the things that you design? And would you really like to be able to understand them better and how they impact your design as far as the thermal effects? It looks like a vast majority of people here do so far. Yep. And that's really what we'd like to show you today, is that you can do that within FlowEFD quite easily. So applications within the electronics industry, we mentioned a little bit. We know that this can happen at the component level within FlowEFD, PCB level, as well as the system level. So at the component level, we mentioned different representation of IC packages. We can do a compact 2-resistor, as well as the Delphi N resistor model. And then as I just showed, we also have the fully detailed Package Creator. We also have explicit models for TEC compacts, a TEC compact model, heat pipes, thermal joints, as well as even LED components where we can look at maximum junction temperature and predict luminous flux. As I mentioned earlier, that large engineering database, which includes a library of IC packages, thermal interface materials. FlowEFD also has the ability to use the SimCenter tester hardware and the SimCenter Terra LED hardware, which we'll talk about in just a couple of slides. We also have things like temperature dependent heat dissipation. You can toggle control on and off of heat, components based on transients, etc. So it's not just steady state. You can look at transient effects with PID control or thermostat control. As I mentioned, the Package Creator. You can see here we have the overall package, but also everything that's explicit within the package that can be modeled. At the PCB level, we saw that we could import EDA data. The material properties can be automatically defined, which is really nice. And we also even have the ability to include joule heating or temperature dependent power. As I said, power toggle on off, steady state, transient effects as well. Also within the same realm of components and at the PCB level, we have electrical elements. Say you have these analog devices that produce a fair amount of heat. Well, we can compute joule heat given the component's electrical resistance, and that can be directly applied to a solid body here where we don't have to explicitly model these things, which oftentimes just isn't necessary. As I mentioned, testing earlier, the tester hardware. This can be used to automatically calibrate and build a parametric study based on your components, and this can really help with creating very accurate simulations in the future. Along with that, the Terra LED hardware, where you want to be able to test an LED get the maximum junction temperature, but also test the luminous flux output as well. And so therefore you can, from that, you can get a really detailed model of your LED to be used within your simulation. And then finally, at the system level, really this is kind of the nuts and bolts of FlowEFD. You have the main physics where we're looking at steady state, transient, as I mentioned, conduction, forced and natural convection, but also radiation, whether it's thermal or solar. And as I mentioned earlier in the demo, you can see that there's really compact fan models where you don't have to include all of the geometry or actually create a CFD fan model with a rotating domain or something like that to show the effects of a fan. We do have some battery models as well that'll be shown in the next webinar. And from there, we have multi-physics, including humidity, condensation, two-phase flow, and even in the electronics realm, we can do broadband noise estimation, as well as particles for dust or something like that. And finally, we can do a thermal netlist output to something like SPICE. And so a couple things here to just jump over here. We have a couple minutes left. So we also have the ability to create boundary condition independent reduced order models, also known as BCI-ROM. And BCI-ROM is a real life process. We can expose challenges for numerical simulations due to complexity and large file size and the time scale. Excuse me. Model order reduction aims to lower the computational complexity of these problems, thus allowing for faster solving while maintaining predictive accuracy in space and time. For example, there's some automotive applications for certain drive cycles and things like that. This is very relevant. So reduced order modeling is an approach to derive dynamic concept thermal model from a thermal simulation, and then that can be used to do very rapid, quick simulations, or quick calculations, I should say, because it's a raw model. And finally, one of the plugins we can also use here is in SimCenter Magnet, which is the solver for electromagnetics within the SimCenter portfolio. And we can use this to calculate electromagnetic power loss that is related to skin effect, if that's relevant in your application. So we'll go into our final kind of technical poll here. And I guess really what we'd like to know is, based on what you've seen today, do you think that the things that you work on and your engineering work on a day-to-day basis, could that benefit from something like FlowEFD after seeing, that this is it's really not your typical electronics cooling analysis tool or your typical your typical CFD tool. It's really kind of the best of both worlds. It has a lot of the features of some very complex and high-end electronics cooling analysis programs that they do require a lot of input and time. At the same time, they offer a lot of the advanced features within the CFD environment and combine them to create a fantastic design tool. So just to finish up here, at a success case, wish I could actually blow this graphic up a little bit. Seiko Epson Corporation, they're designing a projector here, and this projector has a ton of components and a ton of small parts. And rather than trying to pick this apart and trying to decide, okay, which of these components can we get rid of for analysis? What are relevant? What's relevant? What's not? They were able to use FlowEFD to rapidly accelerate their analysis for something like this. So they were able to use for the fan models, lamp units, all of these different types of components were able to be modeled relatively quickly and easily so that they could get their design on the way. And that's really goes to the essence of front-loading CFD using FlowEFD.